Okay, so ostensibly, this is combining content and collaboration and recommenders. Really, it's kind of more of a mixed mode hybrid recommender talk with some practical considerations thrown in and how Solr can play a role. I'm Jake Mannix, and by way of introduction, I'm at Lucidworks now. Your hosters for here. I was previously other places, obviously, and back ages in the past, I did stuff very unrelated to this. That was fun as well, but also not really relevant today, other than the fact that I used to give talks with lots of equations in it. In fact, I used to give search talks with lots of equations in it. I was told that that was a little hard on the eyes, especially in a big conference like this. So recently I've decided I'll not give lots of equations. I'll give lots of Scala code. And apparently that's not any better. So I'm not doing that today. There will not be any equations or Scala code. But I was told that the best talk I ever gave was one that included some of my own art. So I'll make sure that for nostalgia's sake, I'll toss that in later on. It's actually irrelevant, weirdly enough. So keep an eye out for that. Okay, brief kind of agenda of what we're going to talk about. First, justify my existence here. Why are we doing recommender systems at a search conference? So we'll talk about recommender systems as a search problem. We'll go over different flavors of recommender systems. We'll talk about once you've got various flavors, how to mix them together, and in particular, how to then make kind of runtime configurable recommender systems with Solr, because there's some great practical benefits to doing that. And then at the end, we'll kind of talk a little bit about an open data, open source example of playing with recommender systems so you can play at home. Often there are toy data sets out there to kind of build your own recommender systems on, but they tend to be very clean and specialized. They tend not to have both content and collaboration. And the collaboration data, the clicks or views, often is synthetic because people can't often share click data for obvious reasons. But we'll go over Search Hub, which is open data, so you can actually use the data as well to build your own kind of recommender system. It's a very specific kind of case, and if you've heard Grant's talk earlier, I'm hoping everyone did, you heard about Search Hub, and I'll talk a little bit about the recommenders in Search Hub. So, first off, okay, before we jump into recommender systems, like the ingredients to a search system, from my view, in terms of how you generate, how you build a relevance model, how you actually decide what gets served up, is if you want to do search, and modern search to me means personalized search. So when I have this weird acronym there, that's my version of I18N, that's personalization, P13N. It should go with all search products these days, or else you're kind of living in, past century. This century's got personalized search. So if you're doing personalized search, you need to have, obviously, the document text, the full corpus collection statistics. You've got the user query and all of its kind of metadata. You've got the user's history of previous queries and clicks and their general preferences. And you've got kind of the context, like the geography, the time of day, what's on the page currently, what item is being viewed, what search filters may be applied already. And all these things will go into kind of the relevance model for a general search system. Well, why would we do recommender systems at a SearchCon? Well, recommenders really are searches. They're just searches with an implicit query. So they have all the same things that were in the previous page that lead to a relevance model for search, except for the query. So the query is the user's history, their preferences, the current context, and that can be used to generate the same results. So, that's my justification for why this fits in. But in general, the underpinnings of, what goes into a general IR model and what goes into a recommender system, actually at the, not just at the level of kind of what's happening, at the level of what's mathematically under the hood, they're very much the same thing, right? So core IR is doing kind of dot products of these cosine similarities of your query vector with the document vectors. core recommender systems are similarly a dot product of a preference vector with the kind of item vector in the user item preference matrix. It's all just a matrix, man. Take the blue pill, or red pill, whichever pill it is. It's one of those pills. God, it's so dated now. I just realized that. You know, that movie came out in like 1999 or something. Yeah, yeah. Oh. Right, but you know, to kind of hammer the point home, you know, if you have search these days, it should probably be personalized. Everyone's tracking their users. Don't tell me you're not. You have to worry about privacy. I live in Europe now. Everywhere I go, I see the little widget that says, you know, by law, we have to note to you that you are being tracked, and there's a big little thing. You have to close it out and make it go away. Every single page you go on, if you're in Europe, has those. So everyone is tracking you already, over there as well as here. They just are forced to tell you there. Here, we already know it, so just accept it. So if you're being tracked, you might as well use the data that people are using to track you and improve your personalized search. Improve your search by making it personalized. If you have personalized search, you already have all the basic components to make a recommender, so you might as well. And I will go over a little bit of kind of how you can kind of bootstrap your way into that. If you just start with a search system, how do you build a recommender kind of as a kind of recipe-like thing throughout the day. So, brief kind of bird's eye view, 10,000-foot view of recommender system flavors. You know, recommender systems are a machine learning problem. The two different kind of ways you'll want to divide any machine learning problem is kind of what are the kinds of features that go into it, and what are the algorithms that you're going to use. And these are two kind of distinct ways you'll break down kind of your categorized kinds of recommender systems. So in particular, if you want to break down the set of all kind of overview style, set of all input types of features, you've got content-based recommenders. That's where you're actually using the actual textual similarity of your documents, which are now kind of I'll kind of slip back and forth between calling things documents and calling things items in this talk. So just remember, if I say document, that's thinking in the search world. If it's item, it's thinking in the recommender system world. But they're the same thing. So if you've got content-based similarity, you can just kind of say things that are textually similar are considered conceptually similar for the user's purpose. This is not always true, but this is what you do when you're doing a content-based recommender. Collaborative filtering is kind of the more people who bought this also bought this. But of course, it's using kind of just user collective engagement, their collective wisdom to generate a model. There's also other things that people don't really talk about, but it turns out to be a really scalable way to generate recommenders is user interest based, where you build a user model of what kinds of items in maybe a categorized way. So you've got a separate text classifier for all your content, and you've got them all broken up into different categories, and maybe it's a very fine-grained hierarchical category, hundreds of categories. And you've got users who have engaged with different aspects to it, and you don't worry about the fact that they've engaged with individual items specific times, but you know that they've always engaged with sports articles. In particular, always looking at soccer articles, and they're never looking at political news stuff. And you have this preference model built up over the user, not based on the individual items, but you're doing it around the categories. And then you can build a kind of a learning to rank style query model using this user interest to actually do recommendations. Advantages to that kind of approach are that it can highly sidestep the cold start problem, because every item that comes in gets categorized, and then you use the categorization, possibly with weights, different categories that are more probable for that item, to feed it into a recommender model. And then, of course, once you've got a whole bunch of different kinds of input feature types, you can mix them and match them. You can mix them and match them at the level of the input item has a bunch of features that are text features and kind of users that have done them, and then algorithmically work with that. That's an approach that is very compelling from a mathematical standpoint, but from practical standpoints, I'm going to try to shy away from that. So I'm going to talk about a slightly different way to do it in a second. So that was feature breakdown. If we wanted to have a breakdown of the different recommender systems at the level of algorithms, this is just kind of lightning tour of the space of recommender systems. You can consider users grouped together into clusters of people that are engaging with the same kinds of content. They have preferences for the same particular content. And then the way you're going to do recommendations using that is saying, well, if you want to recommend items to this user, just find the users like them and get the weighted set of items that most of those users tend to like. That's user similarity as a recommender. Item similarity is instead saying group together all the items based on the users that collectively engage with them. And now for each user that likes a set of items, they have a set of preferences, find the items like each of those that they haven't yet engaged with and recommend those to the user. Question is why you would use one versus the other. Tends to go in terms of scalability. If you have the typical use in I don't know typical use cases, but often you have many more users than you have items. At least if you're successful, in which case you want to use item similarity, because at the core, at the end of the day, when you say you're using similarity as your method of recommendations, you're building up a symmetric matrix of similarities of the things that are similar to each other. You want the total size of that matrix to be small. So if your users are if you have way more users than you have items, then you want num items squared, not num users squared. There's other reasons for picking one over the other as well, but scalability tends to be the bottleneck there. Other approaches that people use algorithmically to do recommenders, common for a long time, since popularized heavily at the time of the Netflix prize, was doing matrix decompositions, latent factor models. Later, people have done kind of graph-based approaches because really, you may call it a text corpus, I may call it a matrix, someone else will call it a graph. They're all isomorphic. The question is which approach is scalable. These days there are scalable graph-based recommender algorithms. I'm not going to talk too much about those today. And then of course, the flavor of the month for doing anything fancy with machine learning is using neural nets or deep learning. And you can do recommenders with deep learning as well. Also not going to talk about that. In particular, for today, I'm going to focus very specifically on collaborative filtering algorithmically, as well as content-based similarity. That's the kind of title of the talk, using collaborative filtering and content together, and hybridizing those together at the level of input features. At the level of algorithms, in particular, we'll do some latent factor stuff, as well as doing kind of item similarity at the level of text. And that'll be the kind of the pieces that I'm going to put together as my suggestion for if you want to kind of bootstrap your way from your search system into a recommender system. This is the way to go. So let's cook up a delicious recommender system cake. This is my recipe. This is something that, it's evolved over time. Reasons why, I don't know. It's evolved. It's one of these, It's not intelligently designed. It's evolved. Let's just say that. So ingredients to start any recipe, you need to see what do you need to have to start this kind of thing. You need your search logs. You've already got those. Yeah, you've got a search system, so you've got search logs. So your search logs have queries. Hopefully they got something identifying your users. This is helpful. Cookie, anything. It doesn't really need to be something permanently long-lived, because this stuff, it's going to be oftentimes ephemeral. But something to identify your users. The document that was sent back to the user, what action happened? Whether it was just served to them, or was it actually clicked on? Was it purchased? Was it read? Was it saved? Was there some sort of business rule thing that happened there? And then probably also the timestamp, because you want to kind of decay away stuff that happened too far in the past. Obviously, you also have your document corpus, your item collection. And that comes with all the raw stuff. And of course, you've got the kind of global stats, so the kinds of things like IDF and the various stuff that comes along in a search corpus. So those are our ingredients, simple ingredients, just your corpus, your logs. You've already got that. You have a search system. What are we going to use? What do I suggest using? I suggest using a fairly minimalist set of systems to build up a recommender system. Just Solr, Spark, and something to glue the two together and help them out. So Solr is open source. Yay, we like that. Spark's open source. Spark Solr is a library that my colleagues, Tim's around here somewhere. Saw you in the audience. Tim's back there. Tim and his team wrote this set of bindings for Spark and Solr so that you can basically back, a Solr collection can be viewed as an RDD in Spark, and then you can just kind of do your batch computations. It's kind of location aware. It does some smart push downs. It will get even more. It's open source. It's there on GitHub. And come see Tim's talk at 2:50 or so, and you'll hear about kind of doing stuff with, we built, Lucidworks Fusion is built on top of Spark Solr and Spark Solr bound together. So those are all the utensils you need, meaning you don't need HDFS, you don't need a big, huge other set of distributed system stuff, even if your data is big. You kind of need just this. If you're using something else, if you use Hadoop and you still live in that world, that's okay. You could do this too with that, but this is what I would suggest. This is what I like using these days. Okay, so we have our ingredients, we have our cooking utensils. Step by step. First thing we're going to do is we're going to do some pre-processing. So we've got these query logs. So aggregate your search logs by user, aggregate them by document separately, by item, and kind of do some normalization there. So this is kind of one of these key steps that says, okay, you've got some things that are ultra popular, some users that maybe they're bots, so you can filter them out easily. Maybe they're not bots, but they still click on everything and they're not very useless. They're kind of these weird anomalous users that just consume too much of your data. And so you can either throw out the things that are too big, or you can just kind of downsample them. They're not going to affect the results too heavily if you do that. You won't lose a lot of data in items that have a lot of many users interacting with them. If you downsample that, typically you don't even need to be smart about how you do it. Just do it randomly. And that will avoid huge computational bottlenecks later on, because these big columns are bad when they square. And then once you've got these aggregations and you've got these kind of norms, you can do various steps to say, to do the real work of generating this user document or user item preference collection, this matrix that is going to go in to the algorithm. Often generating preferences between a user and an item, often simple statistics is really all you kind of need to do. Just generate, just simple probabilities of the number of times they were presented with this kind of item and the engagement whether or not they engage with it. Sometimes you need to do something more if that's very sparse, but oftentimes counting, log counting, if there's lots of engagement, is really all you kind of need to do. But you still need to think about your business problem here, because you're going to have different events. As we saw on the previous page, we've got different kinds of events, and you're going to have maybe cart ads if you're an e-commerce site, or you've got people saving for later, or they're liking it, or they're resharing, or whatever it is they're doing. But there are some things that matter more than others. A detail pane view is typically worth less than an actual purchase of an item, for example. How much less? That's a business decision. You won't be able to decide this, and in fact, it'll be critical to the success of your product, of your recommender. So once we've got this kind of user item preference set, store it in Solr in a very simple collection that really it's just like a join table. It's just user ID, document ID, preference weight. This is going to be some double. Maybe scale doesn't always critically matter. It could be 0 to 1. It could be 1 to 5, like Netflix style ratings. It's an implicit preference. Empty values are not considered zeros. They're going to be considered unknown. So you don't usually want to have, I don't know, you probably don't want to zero normalize your stuff and have negative weights and positive weights. Often found with recommender systems, trying to assume there are negative preferences often turns out weirdly wrong. You can often consider negative preferences to be the same as positive preferences. So for example, someone really hates the Phantom Menace actually probably means they like Star Wars, right? Like having negative preferences actually isn't always a statement. It's actually, if you don't like something, you don't say anything. You don't give it a weight at all. That tends to mean you don't like it. But if you really don't like it, there's a reason there. So you've aggregated your logs, you've stored this preference matrix, update it over time, maybe decay based on the time as well, and let it evolve over time. Throw away old preferences in the past, but set up a schedule where you're just kind of aggregating those logs over time, and don't let it kind of accumulate too dense, because you won't get much more benefit out of a lot of the kind of extra little weights. You don't want it super sparse, but there's no real practical consideration other than the fact that if that matrix gets to be very, very big, most computations scale as the number of non-zero entries in the matrix. So if you let that scale very big, it's going to take a lot longer to compute your recommendations. Content similarities are also the kind of thing you're going to want to do. Content similarities among your items is not using the preference matrix at all. That's using your actual original corpus. Skipping over the second to last line, essentially this is, you want to do kind of like your just cosine similarities on the document vectors. This often will be slow to compute because it's n squared, but you can kind of think of it like you're more like this query handler from Solr, and just cache them each time you get them in. So do them on the fly and then cache them. But really, there's like a whole talk's worth of stuff about computing item content similarities, and I'm not going to talk about that other than the fact that there are a whole host of research and actual practical stuff out there. So you can do, matrix decompositions on the text corpus itself. That's like latent semantic indexing. You could run LDA and do comparisons on the documents using the topic models. You can use autoencoders. There's a whole host of different things. But the point is, at the end of the day, you have a hopefully relatively sparse matrix. You don't fill in all the entries. You fill in the top entries for each item. And you just have item similarities. Don't worry about where it came from. The important point is that's modular. Once you've got some research group in your team doing crazy stuff to compute item content similarities, at the end of the day, they store them in this thing. You don't worry about where it came from. Store the kind of an algorithm ID of where it came from so you can track it down later, but don't worry about it other than the fact that it's now a content similarity. Okay, so we've got preferences. We've got some item similarities based on content. We need to build some models. So the kinds of models, as we talked about earlier, there's a whole different kind of sets of ones. I'm going to really, I would say, focus on kind of the first and the third. Second one is something that happens, it scales very well. I'm not going to talk a ton about it, but in particular, this thing I'm going to call a simple two-hop recommender. I don't have a good name for it. Maybe there's a real name for this. I'm going to talk about it in detail later, but it's basically literally users who bought this item also bought this other item. And you actually explicitly take that set and possibly re-rank the results inside of it. And if you've got a highly engaged audience, this can be good. So if the average user on your site engages with on the time window that you care about 50 or 100 different kinds of items, and it's not like a very long tail e-commerce site where someone comes once every 6 months and you only get one click from them. But if you've got people that are engaging with 50 or 100 or more, then this kind of thing, 50 or 100 or more, and now each of those items maybe has 50 or 100 people engaging with it. So maybe you've got 10,000 different things in the kind of circle of two hops on the user item graph around each user. That 10,000 item set is now re-rankable. You can do clever things, or even simple things. I'll talk about that in a little bit more in detail later. Maybe I won't, because I'm kind of running out of time. Oh my gosh. Okay. Matrix decompositions is actually the thing that I don't need to talk about the details of it because it already exists in Spark. You already got it there. You can actually just use it. It's actually really easy to just kind of run once you've got this preference matrix. It'll just kind of actually go pretty quickly. Mahout has one as well. It also runs on top of Spark. That's good. Last but not least, you've got item content similarities. You need to generate item collaborative filtering similarities. You don't need to. I think you should, because then you can later on down the line mix them together. With the model you just generated, the collaborative filtering model, the alternating least squares matrix decomposition that Spark gave you, generate user item recommendations with some predicted weight of their preference, and store it back in Solr. Separate collection. Now this is the collection of your things, your recommendations collection you're going to serve to users. So now we've done everything in batch. Everything up to now was all done batch. It's using Solr, but it's using it as a storage engine for the most part. At runtime, you've got this item similarities table. You've got this user item, predicted preference table, where maybe you've got several different subteams at your organization that are computing in different ways. Someone really likes Spark's, MLlib alternating least squares. Someone else says, I'm going to generate recommendations using, I'm going to consider each user's set of items as a sentence that they've engaged with, and I'm going to run LDA over this sentence, and I'm going to do topic modeling over the set of, the user item matrix. Sounds crazy, but it mathematically makes sense, and now you can see whether it makes sense. Store it back in this table with an algorithm ID and see how it works. What does that mean, see how it works? It means at runtime, Solr, you just kind of query the original table that we started with, the user item preference table that was built off of the aggregated search logs. Query some user's preferences with weights. Two different ways to do this. One, do kind of item-based similarity. So query the item similarities table with the set of items together with weights that are the preferences for that user. You're going to return back, you've got the scores of the similarities for each of the items in this other table. And you basically multiply together the preference of the user with the weight of the similarity, add those all up. This requires 2 Solr queries. Still pretty efficient because the first one is just a lookup. Second one's basically a lookup too. It's lookups and dot products, and it's pretty sparse. Other approach is you would think of this as just fetching the pre-computed results when you just query the user recommendations table. But really, because you've maybe had 4 different teams computing this in different ways, you can query for all the recommendations together and take a weighted sum across the algorithms that were in there. Algorithm IDs now provide a filter if you want to just do A/B testing, or you can actually just weight and mix them together. If you do that, the nice thing is eventually down the road, when you've already done this for, say, you've done it for hand-tuned combinations of algorithms, and you've done it for, some, A/B test and say, okay, content doesn't play too huge a role, but if you give it a 10% weight, it's not too bad, and it alleviates the cold start problem. Eventually, you're going to want to actually learn those weights, and you can actually do this now because this is just a set of weights. The number of parameters is very low, and if you want to do, train some logistic regression model to learn those weights, fairly straightforward. Nice thing is this is, you can even have it set up where instead of trying to mix and match these algorithms for every user, you could serve up content-based similarities for new users, and you could use the collaborative filtering for users that are very active. And you just know that as they come in, and just explicitly filter down to one or the other. So that just kind of immediately, without doing anything super clever and having a model that smoothly interpolates between new users and experienced users, you just know that for the new users, you've got content similarity. You explicitly switch between one or the other. My point is that sometimes going with the simpler approach and not trying to build some sort of model that knows how to learn them both is more interpretable. That's the general recipe. Nice thing about it is because a lot of the stuff was done in batch and scales out, the runtime performance is super, super fast. You've got to store a lot of these things in your tables, but if you look at the numbers there, you've got kind of of num items times, say, some small k, like 10 or 50 similar things per item. And you've got num users times num algorithms, that'll be 1, 2, 3, 4, 5, times maybe number of items to serve to each one, 10, 20, 50. So it scales basically as constants times num users plus num items. Not too much storage. Computing it takes a while, so you do need computational power, so distributing this on Spark makes sense. But at runtime, this is super, super fast, which is good. A/B testing multiple algorithms is done simply, mix them together. It decouples computation from serving, and it decouples the people on your teams that do the computation, and maybe your data scientists or your recommender people that run offline from the people that are running the runtime search system, which is often good in many organizations. So I don't have too much time left. I only have 10 slides, so I think we can go a little bit of the details of kind of what that, kind of spiraling in just a second left. Details of what, each of these items in the recipe, matter most, and what are kind of, things that I've learned from doing this many times, kind of things to watch out for. First off, the preference computation. It is, weirdly enough, the very most important thing out of all the steps. Beyond any of the algorithms you do, beyond whether you go item-based or user-based, whether you go, decomposition or classification-based, if you don't build up the set of preferences, because if we're not all Netflix, we don't have ratings. We typically have implicit preferences. If you don't build those implicit preferences right, you're optimizing against some horrible other metric, basically. It requires business product input. This is where you have to know whether or not are you optimizing for revenue? Are you optimizing for return visits? Are you optimizing for engagement? Are you optimizing for what? You need to actually bake that into this process at the level of what you're actually doing to build a preference matrix. How you do that depends on very much your particular product in your organization. Plus, this process involves creating something that will be trained on, so you need to make sure you don't bake in too much noise, because then you'll overfit to it very easily. Okay, that's the most important step. As far as models go, when I call this thing the two-hop recommender, people who bought this also bought this, basically. Not just basically, literally. It's people who bought this, take all the things that they also bought, find all the other people that bought that item, find all their things, aggregate those together. It's the last step that makes this magic, because aggregating them together is the point at which this actually can be a sensible algorithm. Side note, this algorithm also is something you can do on the fly in Solr. With two Solr queries, you can actually do this without ever doing any batch computation. You just have the preference matrix, and you just say, okay, query the preference matrix for the user's interests. Do an OR query across all those for all the other users that queried for those items, and now query back again with the weights that you got from that previous, the scores, and now rank a big OR query there. Doesn't always scale, but on small data sets that can actually be performant. It can be a good way to kind of test out this sort of approach when you don't have a batch computation model. Doing it in batch also makes a lot of sense. In particular, when you really scale out to extremely large size data sets, people will say in the academic literature, oh yeah, this is a horizontally scalable matrix decomposition algorithm. We can run it trillions of edges. Yeah, you can, but no one I know that actually has matrices with trillions of non-zero entries will ever do that. This kind of model is actually how user recommendations are done at Twitter still. You do a two-hop fetch to the neighborhood, and inside that neighborhood you do a very complex learning to rank effectively on picking which ones are the best ones. But essentially all it does is first fetch a little small fuzzy window around each user probabilistically, and then inside of there use features of the user and their past engagements to actually learn how to get what the best recommendations are. But at the core, it's basically just do a two-hop. So speaking of matrix decompositions, because this is essentially the first two steps in a power series of a matrix decomposition, which is kind of funny because this is a matrix. If you look at the way a slow way to do a matrix decomposition, it's actually just taking powers of the matrix multiple times. This is taking the first two powers, so it's like the Taylor series approximation to a matrix decomposition, which is why it makes sense, I guess, in a mathematical way. I promise you no equations, and I promise you art instead. So here I will present you rank K decomposition, acrylics on canvas, my own original work. So it's no math, but that's the model. Don't worry about the math because it's already living inside of Spark, so just kind of use it. It's already in Mahout as well. There's many implementations. Don't rewrite it yourself. I used to love doing this, so I would rewrite it kind of for fun. But unless you're in school, like that doesn't make sense anymore. Like just like Solr exists, as you don't need to rewrite your own distributed search engine, you don't need to rewrite your own matrix decomposition algorithm. Hello. Okay, now we go. Okay, good. Got a couple minutes left. So there's some gotchas. I mentioned computing item-item similarities earlier. Pre-computation is great, but even if you only store the top n times k, you have to compute n squared. That's often big. Even if you only got like 100,000 items in your catalog, or whatever it is, 100,000 squared is big. And if each one is like a dot product or something more complicated than that, then this is really ugly. So there are algorithms to speed this up. Dim sum is an algorithm that was published and then it's incorporated into Spark that does this kind of probabilistic and all pairs computation. The one in Spark doesn't work beyond 32,000 rows though. I don't know why they have that in there. There must be some inner hash map that's certain size that won't let it go. It tries to store it all in memory to be even more efficient. You can do clustering on the items first, and then only compare all pairs inside of each cluster. Sometimes helps. Locality sensitive hashing can make this a little bit better as well, but you have to tune that. Main point of this slide is just computing all pairs of item similarities is often it's really easy to kind of just run your algorithm and then have it never return because it's going to take the next 6 weeks to compute. Other way, when I mentioned like using a more like this cache effectively, is just do this stuff where you actually compute on the fly item similarities by doing, when someone looks at this item, query that item's text with a more like this handler against your whole corpus, cache the results. So that'll actually get the top K results for that, and then now you've got that cache for next time. We already talked about kind of how you do this two-stage two-hop approach. I'm not going to talk about that too much more. Single query approach, doing the weighted sum over different algorithms, kind of already talked about that as well. But I will give a pitch to say that an example of doing all this stuff exists in Search Hub. I won't talk in detail about Search Hub. You should have gone to Grant's talk. Hopefully you did. Some of you were there. But we have code. So there's a website, Search Hub, which is basically search over Apache projects, their mailing archives, their JIRAs, their everything's that's open. We have the code to use Fusion to do both search and recommenders on top of this stuff, open sourced on GitHub, so you can grab that. And it does all this stuff on top of Solr and Spark. And play with it, contribute, because we're actually setting up Search Hub as a resource for the community. So it's both a playground as well as something that hopefully will get better as other people contribute to it, and we get nice recommenders that say, okay, here are threads on the, I can't keep track of, most of the mail archives anymore. The Solr user mailing list, God, it's huge. People asking questions all the time. That's great, but I can't keep up with it. Mahout, no way. Spark, it's just too much. If I could just browse the ones that are most important to me, that would be nice. Help us make that happen. We've got the tools. Let's do it. And so I think I'm out of time, so I will say thank you.